Okay, this is going to be part 2 of the series about integrals using inverse trig functions. Now to begin with, if you haven't done it, I would definitely watch the first video because it gives you some sample problems to get you used to these. And what we'll look at in this video are 3 additional examples, but you'll see that it's going to become increasingly difficult to recognize how the problems fit into one of these 3 forms. Okay, and to begin with, let's go ahead and actually look at the first problem. And the first problem looks like this. Now, you look at it and you have the integral of e to the 3x over 9 plus e to the 6x. Now, when you first look at this, if you go back and look at your choices, you might think, well, how in the world does that problem ever turn into one of these 3 right here? Because at first, it doesn't look anything like it. And that's going to be the problem as you go farther and farther into these things. So all of these things have an integral of 1 in the numerator, but the problem that you've got has got an e to the 3x in the numerator. And none of the problems in that list of formulas have e raised to any power in it. So again, at first, when you first look at it, it looks like there's no way that you could turn it into one of these. So the trick on these is mainly just how do you play around with it to get it into this form so that you can use these formulas. So with that in mind, let's see what we can do with this thing. Now the idea, first of all, is we'll use the same tricks that we did before. This thing is, all 3 of these will eventually require use substitution in some form. And the idea of what I'm going to do is look at it. I can look at the denominator of this thing and think of 9 as being 3 squared plus, and I can change this into something squared. So if I go back to the beginning and look at it, I can come up with 1 over something squared plus something squared. So I'm going to try to get it into this form right here and turn it into a tangent problem. And let's look at how we can do this. And again, it's just a matter of experimenting with them until you hit something that actually works. So the trick on this is this. I'm going to go ahead and make this be the integral, and I'll change it around a little bit. So I'm going to change it from this. I'll put a 1 right here, and I'm going to take this e to the 3x and move it off to the side over here. So I'll make it be e to the 3x over here. Then I've still got my dx. And again, I need something squared plus something squared. So I'll change the 9 into a 3 squared. Then I've got a plus. Now I still need something squared right here. And again, to change the e to the 6x into something squared, remember you multiply the exponents. So e to the 6x would be e to the 3x quantity squared. So you can do it like that. Now what that does, that gives you 2 things. Here is an a, and this thing right here is going to be the u. Now again, if you haven't done it, definitely watch the first video that'll show you how we came across these things right here. So what this is going to be, this is going to change into a use substitution problem. And notice I needed the integral of 1 over something squared plus something squared. And if you go back and look at your derivatives, or your integrals, you've got something that looks like this. Here's the integral of 1 over something squared plus something squared. So I'll be able to use this form now to turn it into some kind of an inverse tangent. So now that you've made your selections, let's go ahead and just finish up with this. Now first of all, you've got to do use substitution on this, just like the previous problems. So we'll let u be equal to e to the 3x. Now you want the derivative of that, so just typical use substitution. So du dx. Now the derivative of an exponential function, it's the original exponential function times the derivative of its exponent. So this will be e to the 3x times the derivative of the exponent, which would be 3. Now I'm going to take the 3 and move it in front, which will get me to this. The derivative or differential of u would be equal to, here's the 3 e to the 3x, and then I'll put the dx right here. Now again, in my use substitution, what I'm going to try to get rid of is this right here. So I need to replace this, and I don't need that 3, so I'll take the 3 to this other side. So I'll have 1/3 du would be equal to e to the 3x, and then I'll have a dx right here. Now again, this e to the 3x dx matches up with this one, so there's my use substitution, so I'll substitute this right here. So there's my use substitution. So again, we'll isolate this all by itself over here. So there is the u substitution. Now when you do that, let's see how it changes the problem. It'll change it into the integral of 1 over, now I've still got the 3 squared plus, and in place of this I'll have u squared, so there's my u substitution, and I replace e to the 3x dx with 1/3 du. So this will become 1/3 du. Okay, next step, take the 1/3, move it out in front. So this will become 1/3 of the integral of 1 over 3 squared plus u squared du. Now you went through all that just to turn it into the form the formula. So now looking at this, let's go back and look at the formula. So you've got 1 over something squared plus something squared. You've got it in this form, so this will turn into 1 over a times the inverse tangent of u over a plus c. So you can use that as your integral. So back to this one again. Let's go ahead and finish this up. This will turn into 1/3 of, and again, a is equal to 3 and u is equal to e to the 3x. So the formula says, first of all, you need 1 over a, so let's go ahead and put that. So it would be 1 over a, which is 3. Then you need the inverse tangent of u over a. So this will become the inverse tangent of u over a, which is, and again, a is 3. We'll go ahead and put a 3 in there. And then finally, plus c. Now in the final answer, you still have to turn the u back into an x. So you can multiply these two together and get 1/9 of the inverse tangent of, and in place of u, put what it's equal to. Well, u would be equal to e to the 3x. So this would be e to the 3x divided by 3 plus c. And there's the solution to the first problem. So again, the tricky part is looking at something that doesn't look at all like one of the formulas that you have. But if you move things around and use u substitution, then you can change it from that into, I think I'll kind of put it in black here and outline it, into this. And this does look exactly like one of those formulas in the list. So there it is right there, and you'll be able to use those formulas. So the trick on all these problems on this video will be recognizing how to get this into that form. Okay, so there's the first problem. Let's try a second one. Okay, second problem looks like this. Now again, you've got the same thing. Looking at this, at first, it doesn't look anything like one of the ones in this list. But it looks a little bit like this top one. You've got a square root of something squared minus something squared. So the question is, can you manipulate it to get it in that form? So what I'll do is this, is using that as a starting point, I'll make this be the integral of 1 over, now the first thing I'm going to do is take this square root of x on the bottom and scoot it off to the side. So I'll make it be 1 over the square root of x dx, and then just leave this one where it was. Here is the square root of 1 minus x. Now the reason you do that is this thing right here, you can think of this as being something squared minus something squared, and use u substitution to get rid of this other part. So again, just a little algebraic manipulation here. I'm going to make this be the integral of 1 over, now I've got the square root of, and to write it as something squared, I'm going to write that 1 as 1 squared. But now I also need to write this as something squared. And if you've got an x, the only way to make it be squared would be the square root of x. So it's equal to the square root of x squared will give you an x. And the only reason for doing that is because you have to write it as something squared minus something squared. Okay, now on this other one on the outside, I think I'll go ahead and begin to change things around a little bit. Let's make this one be 1 over, and this will change into fractional exponents, x to the 1/2 power. So again, we're just playing with things to try to make them line up right. Again, I'll do one more thing before we do the use substitution. Make this be the integral of 1 over the square root of 1 squared minus the square root of x squared. So there it is in the squared form. And this is an x to the 1/2 in the denominator. I'll move it to the numerator and make it be an x to the negative 1/2. And then I've got a dx. Now what this does, this sets it up in the form that you need. You need a 1 over the square root of 1 squared minus the square root of x squared. And if you look at your list of rules, that's going to agree with this one up here. So 1 over the square root of something squared minus something squared. So this is going to wind up turning into an inverse sine. Okay, now it's just a matter of running through the use substitution. So what we'll do is this. This right here is going to be a. This right in here is going to be u. So there's your choice of u and your choice of a. Then in use substitution, what you're going to try to get rid of is this part right here to make it fit in one of those formulas. So with that, let's go ahead and move over and do the use substitution. So I'll let u be equal to the square root of x. Now just keep in mind that means that u is equal to x to the 1/2 power. Now take the derivative of that. So u, the derivative of u with respect to x, and what this is going to give you would be 1/2 x to the negative 1/2. And then we'll move things around. That means that du would be equal to 1/2 x to the negative 1/2 dx. Now looking at my thing, I need a x to the 1/2 negative dx. There it is. I don't need the 2 here, so I'll move the 2 to this other side. So this becomes 2 du would be equal to x to the negative 1/2 dx. And there's my use substitution. So I needed an x to the negative 1/2 dx, and here it is right here. And to substitute, I'll substitute 2 du for it right there. So there's the use substitution on this problem. And again, we'll isolate this in its own little box here. So there's the use sub. Okay, now let's go ahead and change this from an x problem back into a u problem. So what this is going to give you would be the integral of 1 over the square root of, now here you still have your 1 squared, but we'll change this into square root of x is equal to u. This will become u squared. And then finally, in place of this, we'll put what it's equal to, which is 2 du. So you've got a 2 du. Now, next step, go ahead and bring that 2 out in front. So that's going to give you 2 times the integral of 1 over square root of 1 squared minus u squared du. Now, after all that work, you finally got it in the form you wanted, the integral of the square root of something squared minus something squared du. Now, look back at your rules. That exactly matches up with this one, so you can change it into inverse sine of u over a plus c. So all that was done just to get it in the proper form. So what this is going to be, here's the constant 2. Then, in place of this, put what it's equal to. Well, the rule says that it's, first of all, it's the inverse sine of u over a. So this is going to be the inverse sine of u over a, but a is equal to 1. And then you've got a plus c. Now, the very last step is just to replace u with what it's equal to, which will be the square root of x. So this is going to wind up being 2 times the inverse sine, and in place of u, put what it's equal to, so you've got a square root of x right here, and you've got a plus c, and you are done. So again, the hard part of the problem is changing the original problem into this form right here, where it looks like one of the forms in that list where you can find the antiderivative. So the tricky part is going from this to this, and it's just a matter of moving things around and making a careful selection of u. Okay, let's take a look at one more that will involve definite integrals. But again, it also initially will not look like anything in that list. So suppose you have this problem right here. It's got some trigonometry in it. So the integral from 0 to pi divided by 2 of the cosine of x over 1 plus sine squared of x. Now again, looking at this and looking at your choices in the list, initially nothing looks right. First of all, none of these have any trig in them. So you're going to have to find some way to turn this trig problem into one of these 1 over u problems. And again, if you're going to have to be careful about your selection as you go through that. So let's take a look and see how we can go about that. Okay. So we go back to the problem here. Now the idea is this. You've got a 1 plus sine squared, and you can think of this as 1 squared plus a sine squared. So something squared plus something squared on the bottom. If you look at your list, the only one that's got something squared plus something squared on the bottom would be this one. So there's a chance you can turn it into this form, which will turn into a tangent problem. So let's see if we can make that work. Now, how would you go about that? Well, again, it's just a matter of moving stuff around. So let's begin by doing the following. Like we've done in the past, I'm going to make this be the integral from 0 to pi divided by 2. And I'll do the same thing I've done in the past, is take this cosine and scoot it off to the side here. So we'll move this cosine over here. And I'll leave this as, now I think I'm going to write it like this. I'll write the 1 as a 1 squared plus, and again I'm going to write it as something squared. So a sine of x squared. Now why do you do that? Because you need to get it in a form that begins to agree with that list. You need to get something squared plus something squared. Let's go back and take a look on the bottom here. You've got to get something squared plus something squared. So write it in this form, which gets you into a position that you can turn it into this. Okay, now with that in mind, what we'll do is this. This is going to become our a, and the sine of x is what we're going to pick for u. So we'll do a u substitution, and what we're going to try to get rid of in the u substitution will be this right here. So let's go over and do the u substitution now. So on the u substitution, you'll have this. We'll start out with u is equal to the sine of x. So find the derivative, du dx. The derivative of the sine is the cosine, which gets you to du is equal to the cosine of x dx. Again, I'm trying to get rid of that, so here's the cosine of x dx, and I can substitute du. So there's my u substitution. So again, we'll isolate this with its own little box here. So there is the u substitution right there. Okay, let's see where that gets us. That will get us to this. The integral, and this will be 1 over, now here is the 1 squared plus, and in place of this I'll put the u. This now becomes u squared. The cosine dx is equal to du, so I can replace this with a du. Now the only thing I have left to do now is to change my limits. So just remember, the original problem went from x equals 0 to x equals pi divided by 2. But I need u limits. I need to go from u equals something to u equals something. So let's find our new limits. So the next thing you'll do is this. First of all, let's look at the top limit. So when x is equal to pi divided by 2, then u is equal to, and plug the pi divided by 2 into this right here. So this will be the sine of pi divided by 2. Now first of all, if you want to know what the sine of pi divided by 2 is, if you need to, you can draw a quick figure of that. It would look like this. The sine of a 90-degree angle looks like this. I'll just draw a little quick picture of it. It goes straight up like this. So there's 90 degrees. Now if you go straight up, then your x value would be 0, y would be 1, and r would be 1. Now the sine is y over r, which would be 1 over 1, which would be 1. So the sine of a 90-degree angle is 1, so this is going to be a 1 right here. Now let's do the second limit. When x is equal to 0, then u would be equal to the sine of a 0 radian angle. And again, we'll draw a quick little picture of this. So if you had 0, it means it goes off just like that. In this case, x would be equal to 1, y would be equal to 0, and r would be equal to 1. So the sine is y over r, so in this case you would have 0 over 1, which would be 0. So there's the first one, there's the second one. So this is going to be 0. So again, we'll kind of isolate these. Here is where you found the limits. So you went from here, so this little section here is where you're taking care of finding your limits. So there's the limits right there. Okay, now it's just a matter of solving this problem. So what this is going to be then, it would be equal to, now again we'll just change it into the formula. So you've got 1 over something squared plus something squared, and let's look at the formula. And it says it's going to be 1 over a times this tangent right here. So we'll use that formula. So this will break down into, the antiderivative would be, first of all, it's 1 over a. So on our problem, that would be 1 over, and remember a is equal to 1. So we'll have 1 over 1 times the inverse tangent of, now we need u over a. So u is equal to, and again, well, let's just go ahead and leave it as u over a, or we'll just leave it as u over a in this case, which would be u over 1, because we're going to use definite integrals on this. And we're going to go from 1 to 0. Okay, now let's simplify that a little bit. That'll simplify down. The 1 over 1 cancel out, and that just leaves you with the inverse tangent of u over 1 is the same thing as u, evaluated from 0 to 1. So again, go ahead and plug in inverse tangent, plug in the 1 minus the inverse tangent, and plug in the 0. So now you got to figure out which one is. So what this one says is this: what angle has a tangent of 1? Now again, if you wanted to, let's just go ahead and draw a picture of this thing. What it would look like would be this. If I drew a picture of it, if the tangent is 1, you can think of that as being 1 over 1. The tangent is y over x. So if you drew a picture of it, it would look like this. It's got to be 1, 1. You have to be looking at a pi divided by 4 angle. So what angle has a tangent of 1? And the answer would be pi divided by 4 does. Then you've got minus. Now let's take a look at this one. It goes like this. And again, tangent is y divided by x. So 0 divided by, if the only one that could possibly be is if it goes off, you have it straight off like this. So y is equal to 0. You can think of x as being 1. You're looking at a 0 radian angle. So 0. So what happens is what angle has a tangent of 1? Pi divided by 4. Minus what angle has a tangent of 0? That would be 0. So pi divided by 4 minus 0 will give you a final answer of pi divided by 4. So this one took quite a bit of work, but again, it starts out as a trig problem, and the trick is to turn it from a trig problem, and eventually you get it into this right here. You get it into something by moving things around in your choice of use substitution. You change it from trig form in this thing into this form, and this actually agrees with something in that list. So when you look at the list, sure enough, you've got 1 over something squared plus something squared. So the trick to these problems is no matter what you start with, try to find some way to turn it into something in the list. So again, this one started with, this one was a trig problem that turned into an inverse tangent problem. This one involved radicals, and it turned into an inverse sine problem. And then finally, the last one, or the beginning one, this one was an e to the something x problem, and it turned into an inverse tangent problem. So if you just are careful with what you pick for you, and you have to keep looking back at this set of formulas and try to find some way to turn the original problem into something in this list. So these are kind of tricky, but if you work on them and make a careful choice of view, they usually work out.